Chapter 12.5, the area problem. Our goal is to find the limits of summations. In a previous chapter, we used the concept of a limit to obtain a formula for the sum S of an infinite geometric series. So looking at this geometric series, we wrote it in these ways. Using limit notation, the sum can also be written in these ways as well. The summation formulas and properties listed below are useful for evaluating finite and infinite summation. So this is going to be pretty key to this chapter. So make sure that you do write all of these formulas down as we will be using them. Just as a reminder, the I stands for the index of summation, N is the upper limit of summation, and then the I is the lower limit of summation. So we have C, which is our constant. So notice if we have a constant, what we do is we multiply that to the upper limit of the summation. Then we have these here, and maybe you remember them from previous lessons of I, if it's I squared, I cubed, and so forth. And then if you have A sub I plus or minus B sub I, then you can just split it up. And so we will be using these. So let's evaluate this summation. Evaluate the summation of the first 200 terms. And so remember what this looks like is we would start at 1, and then you do the next term plus 2, plus 3, plus ... all the way to 200. So instead of doing that by hand, we can use the formula. So it's just this equation here. So we can use this. So N is 200. So we're just going to write 200 times 200 plus 1 divided by 2. And then I can reduce here. 2 goes into 200 100 times. So we're really looking at 100 times 201, which is 20100. So 20,100. So go ahead and try this example on your own. Evaluate the summation of I squared, those first 10 terms. So the first 10 terms, summing up those first 10 terms of I squared, you would get 385. Now let's start to look at something a little more complicated. Evaluate this summation. We have the sum of I plus 2 over n squared, and notice it's just being written out here. So if it started with 1, it'd be 1 plus 2, which is 3 over n squared, then it would be 4 over n squared, and so forth. And we're evaluating for specific values. We're finding 10, 100, 1,000, and then 10,000. So first what we can do is we can factor out an n squared. So we're going to really just focus on this section here. So let's factor out an n squared. The reason why we can factor out the 1 over n squared, because it's just a constant. So let's rewrite this. This is 1 over n squared, and then we write our summation. And now we have I plus 2. And now let's split this up. So this is I over n squared, and then we have the sum of I equals 1 to n, and we're going to write it as I, and then plus the sum of I equals 1 to n of 2. So now we have 1 over n squared. Now this part right here, we can use the formula. So that formula is n times n plus 1 over 2. And then plus this one right here, it's just a constant. So remember what I said earlier, that you just multiply it to this number up here, the upper limit. So it's actually 2n. And of course at this point, that should be a parentheses, right? You're just substituting using the summation formulas in order to evaluate. So now let's simplify a little bit more. This is 1 over n squared. Now we need to get a common denominator for our binomial here. So I'm going to multiply by 2 over 2. So now I'm going to multiply this together. So this is n squared plus n plus this becomes 4n. And now it's all over 2. So this is 1 over n squared. And this is n squared plus 5n over 2. And then multiplying it together, we get n squared plus 5n over 2n squared. And we can go ahead and factor out an n times n plus 5 over 2n squared. So we can take it on an n. And now we're looking at n plus 5 over 2n. So now that we have this here simplified from what we had all the way at the beginning from this, now is where you evaluate each term that they asked us to. So they said 10, right here, 10, 100, 1,000, and 10,000. So 10, 100, 1,000, and 10,000. So we're looking at the formula m plus 5 over 2n. And so you just plug it in, right? So it's a matter of just doing the math involved in that. So this is 0.75. At 100, it'd be 0.525. At 1,000, it'd be 0.5025. And at 0.50025. So there's some calculator work you're going to be practicing with. Now, just as a check, and you will actually do this in the homework, is you're going to apply the limit at infinity. So the limit, and we're going to use this here, the limit of n plus 5 over 2n as n approaches infinity. So looking at this, they're the same degrees in the numerator and the denominator. So we're really just looking at the ratio of the leading coefficients. So therefore, the limit as n approaches infinity is going to be 1/2. And notice that it is approaching that. So you will have to do a table, plug in the numbers that it asks you to, and then you're going to have to apply the limit at infinity from our previous section. So I want you to go ahead and try this example on your own, eliminate the summation. And so this is what it would be if you were to plug everything in. And so you're just really focusing here. Again, it's more efficient to convert to rational form using the summation formulas to evaluate. So just like we did here. So try that out. So evaluating the summation, you should have gotten 3n plus 7 over 2. Then when you plugged in all the values, I didn't have that copied, but you plug it in, and for 10, you would get 1.85. For 100, you would have 1.535. For 1,000, you would have 1.5035, and for 10,000, that would be 1.50035. Then, given that we know that it's 3n plus 7, so let's find the limit of 3n plus 7 over 2 as n approaches infinity, and that should be 2n. I apologize, that is a typo there. Then this would be 3 over 2. And notice that that is the answer that is starting to come up as the numbers get larger and larger. So I mentioned this earlier, rather than separately evaluating the sums like below, so we could have done it this way, but that's not the way we did it. We could have just plugged in each number and did it this way, 10, 100, 1,000, and 10,000. It is more efficient to first convert it to rational form, which is what we did in the previous examples. Then we evaluate by substituting the appropriate values of n into the rational form and simplifying.